थोड़ी लाइट्स ये होती है दिक्कत होती है।
नहीं सब ठीक है।
आपकी बात
अरे
yes. Anyone tried solving the perimeter of the circuit?
I know the solution exactly what
Yeah, I think so. One straight. Perimeter, anybody? This should try. Nobody? Perimeter, yeah. At least logic, I don't care. So good. Okay.
back here, this is
So, the perimeter of the tree question is you have to print this particular in that order, this particular nodes in that order. So 1, 2, 4, 8, 9, 10, 11, 12, 13, 14, 15, 7 and 3. The way you have to solve it is first you need to print the leftmost leaves, leftmost nodes. The trick is you need to maintain 2 integers at every level. That will tell you how you have come to this particular node. If you have never traversed right, then you are on the left hand side of the tree, which means you can print it out. If you have never traversed left, then you are on the rightmost side of the tree and you can push it in a stack. This piece, or actually just this one. You can push it in a stack, and if you push it in a stack, you can then print it in the reverse order in the stack. And if you are at the leaf, just print it in sequence. Does that make sense? Okay, I'll start solving and then we can. I'll write the recursive function first. So void print perimeter root integer left integer right. First you want to make sure that the root, we will never pass the null pointers, so we want to make sure we don't pass the null pointers, and for that we will return when we encounter leaves. But before that we need to print the left hand side. So if right equal to 0, that means I am on the left side. We'll just print the root data, else if I am in the leaves, if root not root left and not root right, print root data and return. left equal to 0, and right greater than 0, print root data. Sorry, this notes go in a stack. So my stack dot push root data. So this will print your left nodes. This will print your leaf nodes.
So this condition, do we need and right is greater than 0?
Yes, because if your left and right both are equal to 0 at that point in time, again you will be here. You don't want to print
Twice.
your this twice. And then finally we have to recurse. So print perimeter. We are recursing to left first. And since you are going left, you will say left plus 1. Your right stays the same because you are not going right. And then print perimeter root right left plus 1.
So this will not work if we don't have 8, suppose.
It will work. In that case, your so this one will print 4. Correct? Actually, you're right. You can always call this if root left and if root right.
Can you walk through the code?
Yeah, I'll write the driver function first. Okay. So your so we pass 1 from here with your left and right as 0. If right equal to 0, print root. So your 1 is printed. Okay, I'll just start doing this. 1 is printed.
Right equal to 0 is?
If right equal to 0,
Okay.
print root data. Then you are seeing is this leaf or this
Only the easiest explanation is just like a pre-ordered reversal,
Yep.
and we're putting the conditions like which one to display.
which one to display.
Yeah, and then to the right and left variables. If right is actually increasing and left is 0, then you just print those ones.
Yeah.
It's kind of very easy. It's just like if you see like this. The
Yeah,
last
this
one,
is your center node, this is your left, this is your right. Anyways, so you are printing only if your right is equal to 0, which means you are on the left side. Otherwise, you are seeing if you have root, if you do not have children, then it's a leaf node. You print these, and over here, what you're doing is you are pushing these nodes because you are looking at left equal to 0 and right is greater than 0. So for these two, your right is going to be 1 and right is going to be 2. Your left is going to be 0 in both cases. So at that point in time, you will push it into the stack. I think you might print out 15 twice, but I'll have to look into that. You can always pop once before you start printing. So you'll be pushing 15, 7 and 3 into the stack at this point in time in that order, and then you will just start printing it out here. Over here you are recursing going left and right.
So where we are printing the stack?
The stack will actually be a parameter. Stack. And then over here you will print the stack. We keep popping and then
Or you know what, like if we want to have a separate method and don't actually pass back the stack, we can probably put in another condition that if left and right becomes equal
this one.
for the second
This is
time.
only where you are gonna put it in the stack. So
So for printing of the stack, I'm saying like we can put another condition like
Uh-huh.
when left and right becomes 0 for the second time, then print the stack.
left and right become 0 for the second time.
Because for the
When
first-
will left and right become 0 for the second time? They will never become 0 for the second time.
For the first time, like if 0 0 starts from the 1.
Yes.
For the second time, when it comes back and then it's the
It is not gonna come back, right? Why will it come back?
because the stack.
You'll start here. Once this is done, you'll go to the left. Once it comes out of the left after handling this, it will go to the right. It is not coming back.
So
It is not traversing like this. You are traversing like this. You are just printing it in a way that it starts working. Does that make sense? What is finding?
What is my stack? I mean,
My stack. Stack is just, so when you traverse this way, you will actually be pushing 3. You will be encountering it in this order, but you have to print it in the reverse order.
okay.
So I am pushing it into a stack.
no, actually I probably disagree because if you debug it, it goes all the way, and then because every call actually gets in the pushed to the stack. So on the last line, like you see this last curly bracket, it keeps coming back to here until 1. Right? If you debug
Okay.
the code, that's the point actually you can actually print out saying that if left and right equal.
Okay.
You see what I'm saying, right? Does that make sense or not?
I'll debug into it and I'll see. I'm not.
Because
I can't visualize it at this point.
Okay.
That's what I'm saying. It could be right. I'm not challenging it.
okay.
I'm just not sure of it at this point.
Because I'm just trying to keep the method very separate, like instead of
Yes, I understand. I appreciate that. It's just like, any questions? This method is clear.
check. In case you move this if condition, if left is equal to this part, print just after
Left,
print parameter
left,
right.
this guy.
Yes.
So at the end,
Yes. So
Okay.
if I put just a print statement over here
Yes.
for the right node and remove this, it will work and we will be
oh,
because you will go to the bottom of it node and then it starts coming back from the stack and it will start printing.
Now, by the way, just record like your case solution by K.
Yeah.
I tried it work actually. We just have to tweak a little bit, but it was working.
Yes.
The N largest.
oh, okay.
It's like a 3-4 line code.
Oh, okay. Cool. And we can do that after this. I don't have to redo the things. So now, first we'll go through two small functions and then I'll use those. Given a binary search tree and a node, find the smallest value of that particular node.
Smallest value means like
If I give you 8, you should give me 1.
go to the
Leftmost.
Okay? What happens in this case?
Still
Leftmost.
left.
What happens if you have this?
Leftmost of the first one.
It
So
should
the
be
root
root.
Okay.
is
Root is-
Okay.
root itself, right?
So how will you write that as a in code? Yep. Because it's pretty straightforward. I just want one will use it. I'm going to use this particular get smallest node star root, if not root.
And then if root dot left is equal to null, then print root.
If not root left, not root right.
No, we don't need
Why?
right.
We don't need this.
No. The first one was right. The root arrow right, you don't have to check.
Yeah.
Because always.
But
root
if you are in
arrow-
a leaf, if you are on a leaf,
Yeah, so leaf is
So leaf root node will be the smallest one.
yeah, but what if I give you a single node?
Single node also in that case also if left is not there.
Yeah,
that
but
is
then
the
if
node
you,
will be-
if I have, if not root, okay, if I don't have this condition, I will recursively call it for the left one. Just bear with me for a minute.
Yeah.
Okay.
I think I can, these two are the same line, I just, that should be a way to minimize it.
So I still say there that we don't need root
Root
arrow
right is
right.
not required.
root arrow right.
Yeah.
Okay.
If you run through it like in the tree over there, let's believe that this is the tree, right?
Okay.
And this part is not there. So still the smallest will be there. If I remove this part and run this code, it will be done again.
Okay. Anyway, so this is clear. So we have in our node gets smallest. Create parent.
Parent of the smallest.
No, just pause. Sorry. So you are given a root and a child. You have to find the parent of this child.
Let me think for it.
You give you the first line. Anybody?
This is binary tree or the binary search tree?
Binary search tree.
I think we just need to pause this and I need to visit transition right. Root dot left and then copy them as the same child.
You are not returning true or false. You are returning the node. So you can't have an OR.
Oh,
You can take a temp variable.
yeah, I can do that in that way.
Just take a temp here. And if temp, return temp. Otherwise, go down to it again. Yeah. do it for binary search tree.
Yeah, in that case you need to compare it with less than only.
And you'll be reducing the time to travel, correct?
Yes.
You don't have to go both ways.
Right.
Only this one changes.
Check if it is greater or less than only.
So yeah.
And what happens to that, like, when there is, so in that condition, we are not handling if the child doesn't exist in that particular trip.
Yeah, you will be handling at the end return false. So he had an if temp,
Yeah.
return temp, if temp, return temp, at the end return null. Because if it is not on the left hand, if you look at it from this perspective, if it is not on the left hand side and not on the right hand side, then it doesn't exist. We just return null. Okay, so if what was I saying? Okay. If child data is less than root data, return get parent which figured us left or right. And return return root right. Do I need it here? Don't think I need this one. The compiler might complain. And it is
Thinking.
okay. You have to delete a node from the binary search tree. And there are multiple ways to solve it. The way I solved it, I use these two functions. That's why I solved them first. How do you?
Simple ways like those three conditions. If there is one child exists, or both child exist, or no child exist.
Yep. Okay. So, which one do you want to handle first? If no child exists, should be pretty straightforward. First of all, if not root or not delete, return root. So we handle the,
So why are we returning node?
because if I were to give you 8 as the root and 8 as the delete, then your root changes. So you are returning the new tree to me. Delete. Or you can pass double pointer to the root, because you are essentially changing the pointer to the root. So delete leaf. So
So basically the logic is that we are first finding the gate parent at that node, and if gate parent has a left, then we are making the left.
So you have to handle multiple scenarios. I'll walk you through them.
So what we are saying that we are taking 10,
Okay.
and if left exists, then make left as the parent, and then 11 will be the right node and left will be null.
Okay. If left doesn't exist,
And if left doesn't exist, then right will become as a parent, and so this entire thing will go away and 11 will come in that case. Right? And if both does not exist, we don't have to do anything, just delete node.
what if your right has a left?
If 8 need to be deleted, then we need to change them.
No, that's okay. If I were to ask you to
If the-
delete 12, how do you solve this case?
We'll take the 13. So we move one right and then all the way left. So actually there are two ways actually. Either we go one right and all the way left, or we go left and then all the way right. Any of the two not fit in that the 12 spot.
Okay, so then which way will you go? Which way you
I think usually people actually go right and then all the way left.
Okay, so then what you are saying is whichever node you have to delete, you have to get the smallest from the next one.
Just go one right.
Yeah.
Take a right.
The right one.
Right.
So
and
you'll
then
be
all the
passing
way-
node root right to this guy and whatever you get.
Right. And then all the way
Okay.
left, right.
And if you have left child,
or 40,
let's say you want to delete 4,
so we want to delete 4, then 5 will fit.
then 5 will fit, are you sure?
Yeah, 3
3 will fit?
Yeah, 3 and 5 both will fit.
with
So
the
we
same
can-
logic. So I
Left
like
or
there
right?
are two left two reasons, right? So there are two logics.
Okay.
Either go left and then all the way right, or go right and all the way left. So
Okay.
3 and 5 both fit
So-
over there. We can follow any
3
of them.
and 5 will both fit over there, okay. But won't you be disturbing the tree and at this level and this level?
This tree will get disturbed. Disturbing me in
So what if instead of, if I'm removing 4,
right.
if I just start, so what will I do over here if I have to remove 4?
So what he is saying that if you have
Replace
to
the-
four in this tree, go to our right.
Okay.
Whichever is the
Three.
node, pick that,
Uh-huh.
make it over here,
Okay,
and
you
then
bring
we will
3 here.
3 here and then delete the 3.
Okay.
and everything is correct.
And then delete the
Okay.
3.
Delete 3. Okay. So you are getting the, what value are you getting? You are getting the largest from your left.
Yeah.
Largest from your left, and if left does not exist, smallest from your right.
Okay.
And make it.
Okay.
That one.
Right. You want to write it?
That's okay.
Come on.
So we will have to create two functions over there,
Yep.
like one get smallest, get largest,
largest.
and use that.
And get parent as well.
I think like we don't have to write
Okay, fine.
it. So we can just directly write the whole code in that one.
Okay.
So I'll explain the scenarios again.
Okay.
So the one scenario is like we are deleting a 5, the leaf node. So for the leaf node, we just like delete it, we do nothing. And the other scenario is like this one, where we have
So how will you delete it?
delete. If
Make
you are
the
using pointers,
Parent.
Yeah, if you are making it delete, your pointer, your parent still has a reference to that.
yeah, we say parent
Get
dot
parent
left.
and make it static.
Because
You'll have to do a get parent, right?
Yeah. Yes.
We have to do get parent.
Yes.
Yeah.
Because your parent has a reference to that particular node.
So make
If you
the
delete
parent
it,
We
size
can do
like-
get parent, or we can have one extra parameter over here
Uh-huh.
to like keep track of the parent. You see what I'm saying?
I am not giving you parent, right? The main function doesn't have parent.
So the main function is going to pass me
Just
for
the
first
root
time, parent as a
and-
null. Parent as a null. So as we go further,
Mhm.
we keep making the previous node as a parent.
Oh, so you are going to traverse the tree first.
Yes, it's gonna be a recursive method. So
Oh, okay.
we can keep calling delete
Sure.
that, and then
Go ahead, no problem.
okay. So we'll probably add the
Just the eraser.
and then start from- So if why do you these two actually? We just like start from the
Like you need to know which root, which node you are deleting, right?
right. This is going to be an integer data or okay we can
Anything is fine.
okay.
Pick whatever.
So if the let me put a symbol okay.
Mm-hmm.
So if
Check it, don't be same as delete. Right? Delete node.
You don't have to like check for it, but
You don't have
you
to
can.
traverse or-
Okay, you can
so
check for it.
if delete node actually is
Equal to root.
equals to root or like let me start from the
Okay,
definition.
sure.
If the left equals to null and right equals to null,
Mm-hmm.
then we want to say
Parent of delete.
is everything clear? So for the first time purity will be null. So we want to get to the
Don't try to solve it with the recursive approach and then same thing. Just traverse till the delete node. It's get parent.
and make it make it percent return also. So I'll say like get parent over here. As
Okay.
you were saying.
You're gonna use that condition like even if let's say you're trying to delete 5, you're gonna run through that code 5 n number of times. How many nodes you have in the parent? Because your file A has left and right both null.
There is a get parent delete and we get the node of
It's parent.
and now we say if both are null
Then just
Then
delete
we
it.
say like yeah delete that node we say like
Parent dot
parent dot
Dot child.
so we want to say like if
right or left.
yeah right or left if two dot left
Yeah.
equals to delete then we make this one as
No.
null. As we say
Three
like
dot right.
yeah right equals to null. So that's the first condition and the second condition is
If you don't have a right child.
It doesn't have a child. I mean, you will get null, right? You are not even checking the condition of the parent.
the same thing like this. So for example is null so b dot left equals to null then
No. What I'm trying to say is the child that you're trying to look for delete node doesn't exist. Your parent will be written as null, right?
If P is
If
null,
I say
then what will
delete, let's say
and
100.
we'll actually get to the detailed condition later on. Let's actually take the pseudo
No, but that's a
But
basic
still-
condition, right? I mean, I'm trying to ask you to delete the node 100, which doesn't exist there, so your T will be null. So,
yeah.
If P
Okay,
is
so
null,
if p
then
equals to null, then just say return nothing null. Okay.
yeah.
So let's come focus on those three conditions. The first condition is like both are null, so that's taken care. And the other one is like if delete dot. So now we want to say like if this delete node
As both left and right.
has
one child.
one child.
Okay.
And so what we want to do is we want to take this
Parent
pointer
dot-
and start pointing over here. Okay, the same way like if it is on this side, then we'll point over here.
So can you think of it like this? If you have a left child, you're finding the largest node in the left and you're deleting it from that tree.
So we just simply point this one over here and then delete this one.
Yes.
There's a condition like where a parent has
A left child.
Right.
And you're getting, okay. So if your parent has a left child,
Right.
okay, forget this tree. What are you doing? You are taking this from this tree and you're deleting it.
I'm just saying like
You are deleting it, right?
Yes.
Because this will become over here.
yes, yes.
So from this tree's perspective, you are removing this particular node, you are deleting this node,
yes.
and you are updating the node. Can you recursively call delete node? And the node is going to return you the root. So you can replace this to 2 and say, hey,
Deleting this node.
yes.
Hang on.
So you replace, so this is your original condition, right?
Right.
3, 2 and 1. This is your step 1.
Yeah.
Okay? What you are saying is, instead of 3, you will make it 2. And over here, this subtree, you will delete this, and whatever is the updated tree, you will start pointing here.
I'm not replacing the data actually. I'm just saying like
Okay.
the parents.
That's what I did. So I called it recursively.
Okay.
Replace this data, called it recursively, whatever it returned was the root. I just started pointing to the root.
Okay, so you don't have 3 conditions then.
I have 2 conditions.
But okay.
Because when I go to the left, I need the largest of the left. When I go to the right, I need the lowest of the right. So there are 2 different conditions there.
Okay.
And your leaf is the break condition.
Okay.
Go ahead, no,
Yes,
you're doing
yes,
it.
actually.
Huh?
So you are replacing, right? So
Yes.
when you are replacing,
Because the
are
thing
you
is that
doing
parent
no, no.
can be expensive.
So if I do like if I want to delete 13, so sorry, if I want to delete 12, right?
Mhm.
So in that case, I need to find 13,
Mhm.
and what you are saying is recursively you call.
No, I'll first.
Then you will find the 13 and replace with 12 and delete this
Yep.
13. Okay,
So there, one question again the same I asked again. We are returning node star, right?
Mhm.
So which node we are going to return?
The root of the tree, the new tree,
Then you
the new root. So I'll leave this as is. Tell left. Just get the data. So we get int temp equal to get largest your root left, correct? Then data equal to temp, then left equal to delete node root left and temp. Or I can do similarly, if del right, I will do node star temp equal to get smallest root right del data equal to temp data del right equal to delete node stupid. You don't need this condition. So if it's a leaf, what you're doing is right, you are getting its parent and then seeing which one is it this parent's left child or the right child, and you're making that reference as null. This is fine. If it has both left and right, then you're giving the preference to the left. Mine, I do it this way. You're getting the largest from the left hand side, you're replacing it over here, and then you're deleting that value that you just got out. Since that is a leaf, you know that in the next iteration you are gonna get rid of it. So this is gonna recur fully twice. Make sense? It took me a while to think of this.
Why we are not checking delete right? It gets smaller.
So you are seeing if you have both left and right. If you don't have both left and right, means either it has left or it has right.
Yes.
If it does not have left, then it has to have right.
So it should be else.
No, you don't need anything. If
It's returned.
it goes inside, it will return.
Oh.
I will be doing that. So there will not be return because I write to coding project
Oh,
in my reference, so that's why.
Oh, okay. Then
But in recursion we need to return without.
No,
recursion,
no.
you don't need to return.
Reference by reference to victim object somewhere.
Doubts, questions? I know this solution is a bit. You have to make a leap of faith that yes, this will delete that.
For this solution we need to have largest and smallest. That means we are traversing 2 times to find largest and 1 time to find smallest.
No. So
The second approach, what we are saying is just replace the pointer instead of replacing the data.
that is what I did. I'm replacing the data. I'm not replacing the pointer.
No, I'm saying is replacing the pointer. Wouldn't that be faster than?
Yeah, you can. You can do this. But that will, you can do that only in the case of left,
No, but for both cases we can do.
right? How can you do that?
Like we just need to replace the whatever the parent is. We just need to replace the parents. Either make parents left as deletes left if left
Yeah.
exists. Otherwise make it as a right one.
That's what I've done. Right?
So
you're
you are
not getting
replacing
the
the
point.
data. I'm saying we can.
You're
replace
replacing the
pointers.
data and updating the pointer as well.
Yes.
Okay.
What I'm saying is we don't need to go for largest and smallest. Just we need a one function get parent.
Okay.
And based on the condition, we could replace the pointers. No need to find the largest and smallest.
Okay, let's see. So if you were to replace, you are deleting 12, you find 8, and then you point 8 to,
We are replacing which one?
you are deleting 12,
Okay.
and you found the parent as 8,
Yes.
then you would, 8 right would look like, what would 8 right?
One question.
Well, let's finish that.
So if we need to delete 12, new parent would be whatever the 12th child. Right? The 10. So 10 would be then instead of 12 there would be 10.
No,
No. Then also have a child.
Because 10 will also have children.
So these children need
Because 10 will have both left and right child.
Yes.
Once 10 comes in place of 12, then it will start either having 3 children.
No,
This
we
is
need
not
to,
allowed.
we need to adjust it.
Yeah, so exactly. So instead of having to adjust it here, going more than one node below, you have to think, okay, there is something wrong. I need to rethink.
So I understand what Faisal's problem is, and let me explain you. Your problem is
Yeah.
like
What was your question?
you are
No, I
making couple
I
of
got
times
it.
the cursor, right? Like traversing the entire tree 2 times.
Actually,
one for
no.
get child and second for the
So
get
if I have to
small
delete
and then
put it right.
Yeah.
no,
So
so the cursor
the-
will always the traversing
Okay,
for
this
entire
tree
tree
or
which
the
happens
previous tree?
because once you will
Tree,
reach
okay,
the
yeah.
parent,
You have to delete
at
this
that
tree.
time the further traversing will stop, right?
So what you
Which
do
means
is you get
you
the
start from
largest
eight
from here
and start finding the parent.
to
The moment you will reach till 12,
then
you will stop,
pointing to
right?
one.
Because you found the parent and you are not going
Let's
below.
say 12.
In the gate is smaller,
Yeah, delete
you are
that.
starting from 12.
You are both
You are
left and
saying
right.
that whatever is
You're going
below it,
left.
Just
Yeah,
find
so-
it.
you find that.
Yeah.
You are always
Yeah.
traversing for the
Yeah.
entire tree happening once.
8, 9, okay, yeah, we have 9 here.
We are not looking the complete
So
tree again and
you
again.
get the largest,
11,
which is
which is
11.
11. You remove 11,
11.
make this 11.
You don't remove 11, right? You call the delete function.
Yeah.
So okay.
Okay, so you make this 11.
You have delete node, root dot left,
Mm-hmm.
but root is
Root is left 10
How?
because you are in, okay, you are here, correct? You want to delete 12. Does it have a left child? Yes.
Yes.
So I'll say find me the largest, this 11.
11. Yes.
What is the largest in this particular tree?
11.
11.
So I found 11.
Okay.
I'll say replace this with 11
Yes.
and then I'll say delete from you, delete this
No.
node.
See, delete root dot left.
Yeah, so delete, oh sorry.
That's
what I
One-
want.
sorry, fine. This is, yeah, and I have multiple nodes, I get confused. Then left, then left. Then- yeah, sorry. Now is it clear? Fine, nice. it's a break, so yeah, coffee, anything. Is it really difficult to understand? Like even in break, you're scratching your chin. If you have questions, please feel free to ask me.
Correction, we are passing new route, so that's.
Yeah, because every time you are returning the root of the tree from which you deleted the node.
So that means this time when we call, what we should do?
No, this root is the root of the tree. This root will be the root of the new tree that is formed here at del left.
But every time we call delete, this root will be updated.
Yes.
So we are then again turning this. Why do we?
Okay. So let's say I were to give you 8 and 8. Correct. So your root is going to get deleted here. Right? What will be the new one? And according to this, I will pick up 7 and then create that. So you are returning 7 in that case.
Yeah.
We are returning 7 from this point. Now I know I am not deleting the root, deleting the node itself, I'm just updating the node. But just to be on the safe side, I return it in case I wanted to delete the node itself, the whole entire. Am I making sense? So when you call it recursively, over here you are passing del left. Which will get, yes, which will be the new root of this guy. So in that case, when it comes out, it will return the del left, but when it comes out from the stack, I will still have my root, the original
New root
root.
will be there.
No, this will be not the new root.
No, whatever.
This is whatever this root over here, that's what it will be. This will bring its own root,
Yes.
and that it will bring you to del left.
I think it will have new data though. The root will have new data, right?
Yes.
Yeah.
Root can have new data. It's not necessary that it will have new data. If you are deleting
Yes.
11, then it will not have new data.
Yeah.
You still confused? Okay. So on the stack, when this gets called recursively, what will happen is the stack will actually store all the data it has, and then it will pass in new data. So the first instance of delete node, root is 8. The second instance of delete node, the root is, let's say you are deleting 12, then the root is 12. Third instance, if there is any, it will be 10, 9, 8, and then when it will start returning, this will keep going away.
I'm just getting sucked into that whole precision thing. A little early.
If you actually look at the guidelines,
Well, alright, hold on. Right, yeah.
yeah.
Right.
इसके बाद
Picking up leaves on the guy's driveway, I'm like, dude.
I can probably, the thing that I have in my mind, I can probably put it over there. Now. So it's kind of really different, I think. Instead of recursion, you just have to put like 3 conditions. Like the first is already there. If the node could be have both the child and null, then do that part. And then there is a, if you have one part null, then you can only actually say. I can read that one, right?
Sure. Everybody is cooperative. Black.
So that was the first condition, like when both of them are null. So simply like leave this one. The second condition is with this if else is del dot left equals to null or one, which means like one of them is null.
Yep.
That would also be null or.
No, it's handling the first line.
Yeah. So if one of them is null, then now we want to know like which side, like if the node to be deleted on the left side of the parent or on the right side. So if it is left side, then we simply say d dot left equals to
That.
del dot. We don't know like which side you want to take. Like if one is on this side, right? If this is null, then we'll make this one over here. If this is null, then we'll put the pointer over here. So we want to say, yeah, again, I think like if right is null, then take the left side.
Or give the right side.
Or keep the right.
Okay.
Okay. And the other condition is if the node to be deleted is on the right, is the right side of the parent. So we'll say like if e dot right equals to del and then e dot right and same condition over here. And the third would be like both are not null. So we again put a else. And over here,
the second condition also, you are not taking the minimum or maximum, right?
Why you need?
why you need
Why you don't need it?
One maximum.
So if you want to delete this one, you simply put this point over here. If you have something over here, simply put this point over here.
Right.
Make sense?
Yes.
You have only one side. You start pointing to that side.
So you
How
always
are
have
you
to
getting to know that it has only one child?
That's what you did, right? If this is either null or null.
But that one can have further one, further.
Yeah, it doesn't matter, right?
So we are starting from the point where we have always a parent and a thing to delete. So in this case, we have this is parent and this is a delete, right? So we always know these two entities anywhere in the tree. So if you want to delete this one, and then the delete only have one child, it's very simple. You just put this pointer over here. If you know this side, put it over here. That's what these conditions are doing.
Okay. And what if you have both?
Both is that.
That's part of the thing.
If you have
Yes.
both,
If you have
I'll just get the smallest from the right.
let's say like we have this as a parent and this one as a delete one.
Okay.
So what we want to do is go one right,
Of parent or delete?
sorry, of parent, one right, and then all the way left.
So you are getting the smallest on the right hand side.
Yes, put 5 over there.
And
There are two ways to do that.
Yeah.
Either go this way or go this way and this way.
Yeah.
Now let's assume that this 5 was not there.
Mhm.
We go one right, this left is not there, let's put 6 over there.
Yeah, so you are getting the largest from your right hand side, smallest from your right hand side.
So that logic is small